So my name is Andreas. I work at Tweag by Modus Create, and today I'll take you through our journey with building Haskell with Bazel and Buck2 as well now. So to provide a little bit of background here, Tweag was a place where early on we were interested in Haskell and Nix and sort of functional programming and correctness and purity and hermeticity and all these things. So when Bazel was open sourced by Google in 2015, that certainly caught our attention. And at the time, a little bit later, we also had a Haskell project going on that was reasonably complex, had some C code, some code generation, some other complicated pieces, and was generally just hitting a scale where the native build tooling Cabal was running into its limitations. And so we were looking for other alternatives. And of course, Nix was one of the things we considered, but sort of it's more on the package level, a bit too coarse-grained for what we wanted there. So we started looking into Bazel, and that is how Rules Haskell came about. And there is a blog post that you can read more about that from back then. And before I continue the journey, I'll first want to take you a little bit through the very basics of how Haskell builds work. So there's a bit of a Haskell builds 101. So as many languages do, Haskell has a notion of modules, where a source file corresponds to a module. And then these modules can import other modules, which sort of incurs a module dependency. So here you can see an enterprise-ready hello world, where you have a say module and a hello module with a message, and then a main module that imports the say and the hello. And that gives you this module dependency graph. And now in order to compile this, let's start first with the say module. We take the source file. We pass it to the Haskell compiler, the glorious Glasgow Haskell compilation system, if you ever wondered what GHC stands for. And that produces two outputs. One is an object file. It's the same kind of object file you would get out of compiling C code or something like this. And then you have this .hi file, which is called an interface file. And that is sort of like a generated header file, kind of. It contains like signatures, exported symbols, and a bunch of other information. But it's exported, like it's generated by the compiler. If we now walk through the full compilation example, again, we're compiling the say module, and then in parallel, we can also compile the hello module. But the important thing now is that in order to compile the main module, we need to provide those interface files because the type checker needs to know what symbols were exposed and what types they have and all that kind of stuff. And then we can proceed from there. We also get our outputs from the main module, and then we can link the objects together and finally get our executable. But the important takeaway here is that in order to compile a Haskell project, you need to compile the modules in module dependency order. Otherwise, that's not going to work. All right. So let's talk a little bit about incremental builds. Broadly speaking, if you have a build action dependency graph like this, and you have some change indicated in red here that impacts this action, then what we want is that only those actions that are impacted by that change are invalidated and rebuilt, and the rest stays the same. We don't have to rerun this, right? Incremental builds. And of course, Bazel provides this with clever hashing and caching and all these good things. Now, if we look at the way that Rules Haskell works, in Haskell, we have this notion of packages, where we take a bunch of Haskell modules and we bundle them together into something called a package. And for the library case there, we have a rule in Rules Haskell called Haskell library, following the common Bazel patterns that has a name and a sources attribute, and in the sources you pass in the source files for all the modules that make up that particular package. And then the rule under the covers uses the Starlark API to generate a build action, forward those module source files, and invoke the Haskell compiler to build them. But the problem that we see with this approach in Bazel is that now we don't get our incrementality at the module level, right? If we invalidate one of those modules by making a change to it, even if it's just a comment or anything, we're going to have to rebuild all the modules in this package. And the reason for this is that we are nowhere are we exposing the module dependency graph to Bazel, but Bazel would need to know the module dependency graph in order to get incremental builds at the module level. And Bazel cannot infer the module dependency graph automatically for us here. And the reason for that is that Bazel's build graph is completely static. So at analysis time, when all the rule implementation functions run, the action graph is written, and you don't get to look at anything generated at that point. And so you cannot infer build actions at that stage. And of course, there are good reasons for this, right? We want our queries to be fast. We don't want, if we run a query for, I don't know, target determination or something like this, to have to build half of, Google's monorepo or something like this. That would be a problem. And of course, we also want things to be explicit. We want an explicit target dependency graph. And so Bazel decided, no, we're not going to do any dynamic dependencies, asterisk, but at least for the purposes of a rule author through the Starlark API, it's completely static. Okay, so we had this issue. We wanted module granular incremental builds, but we didn't get them. So we explored some other alternatives, and one of them was persistent workers. So Bazel has this feature called persistent workers, where you can spin up a compilation server that is then served requests for build actions and then can reply to those with the build results. And the idea behind this is, let's say you have Java-C, spinning up a Java compiler needs a JVM and everything. That's a costly operation. You also want the JVM to be hot and all that. So you want a persistent compilation server for those compilation actions. And so Bazel has that concept of persistent workers for that purpose. And we thought, well, this is a persistent thing that could be a place where we could store the necessary information to get the module incremental builds running within a build. So I see, faces. I know. And so we explored this option, but of course the downside is that we'd effectively have to re-implement Bazel's caching, and there is a whole lot of problems with potential introduction of inhermiticities and whatnot. So we discarded that option. It was just way too complicated. So then the next thing we did was to say, well, if Bazel needs the module dependency graph in order to give us module incremental builds, we are going to give Bazel the module dependency graph in the build files. So we introduced a new rule, Haskell module, that compiles a single module. But of course, you have a lot of modules, and these dependency graphs change relatively frequently. And so that's a bit of a hassle. So we introduced a Gazelle extension that then generates these module dependency graphs and exposes them to Bazel. And that works, and you can use this today. And you get your module granular incremental builds as you want them. But there are some downsides to this. So if we then look at our build files, they get a little bit noisy. We end up having a lot of module targets in there. We have to make sure they're kept up to date. So if we use Gazelle, there's always this Gazelle pre-step that we need to run before our builds or when developers make changes. The diffs get very noisy whenever the module dependency graph changes, and that happens more frequently than that the target dependency graph changes. And Haskell also supports the C preprocessor, and that is often used for cross-platform projects to guard imports. And trying to have Gazelle automatically parse CPP logic is not a thing we were going to do. So you always need a little bit of manual fudging to make this work in many cases. So overall, still not ideal. So when Buck2 was then open sourced by Meta in 2023 and had a form of dynamic dependencies, we were very interested and wrote a blog post about sort of comparing Buck2 and Bazel that goes into a few more differences than I'm going to cover here today. And then in 2024, we were fortunate enough that we got to work together and still are working together with Mercury, who are also in the audience, on building Haskell with Buck2 in an efficient way. And so what does that look like in Buck2? So Buck2 also uses Starlark as its configuration language. It also has something like build files. And rules are sort of often using very similar or the same nomenclature. So there is also a Haskell library rule. And that has a name attribute and a sources attribute. And we're going to pass all the module source files of that package to the sources attribute. But in this case, we are going to get our module level incremental builds for that target. And the reason for this is that Buck2 is able to dynamically infer the module dependency graph just from this input in the build file. And the way this works is through dynamic dependencies. So I'll walk through a little bit how this works. I'm going to give a high-level illustration here, but the idea is that on the very left in this picture, we still have our three source module files, say, hello, and main. And then on the very right, we have our main executable that we want to get out. And in between, we have this big box that takes those inputs and produces that output, but we don't know exactly how yet. And then there is this other special input that I've marked in purple here, that runs GHC-M or like equivalent of GCC-M, some way to parse the source files and produce a parsable file that contains the module dependency graph. And we get to pass that into this dynamic action. And then this dynamic action at build tile in the Starlark code can read the output of that action in, parse it, and then use the regular Starlark API to generate new build actions that take this module dependency graph into account. And then at that point, we're sort of dissolving this, this big box and placing in a module granular build action graph. And from then on, all the regular build rules apply, and if we make an incremental change to our inputs, then we're going to get the incremental build on the module level for our package automatically at that point. And so if you're wondering, this is what this looks like in the Starlark API. So within our rule implementation function, there is a special action called dynamic output new, and presumably at some point in the future, just dynamic output. And you pass that a dynamic actions object, and you create one of those similarly to how you define a rule. There's a global function that you call, and you give it an implementation function and a set of attributes. And then this dynamic action has an implementation function, and in there, these special inputs, these dynamic inputs, you get to parse them or look at them. In this case, there's the read JSON, and also I think it's called read text to look at the raw text if you want to. And then afterwards, you can issue new actions based on the information that you get out of that file. And now earlier I was talking about how Bazel did not do this kind of thing because they wanted to make sure that the queries are fast and the target graph is explicit and static and all that. And so you might wonder, well, where is this leading? Surely Meta also has those concerns. And they do. And the idea here is, though I hear checks of this are sort of in the works, let's say, but the idea is that the inputs to your dynamic action are statically known. And the outputs of your dynamic action that are generated as part of the dynamics action are also statically known and scoped within the target. And you only get to wire those pieces up dynamically. But the scope of inputs and outputs is statically declared. And then what this is there to ensure is that the target dependency graph is static, so that you still get your fast queries and explicit target dependencies and all that good stuff that you want. But at the target level, you also get the ability to dynamically generate fine-grained incremental actions. All right, so we did that, and that worked perfectly. But then there was another piece that we ran into that I want to talk to about a little bit, and that is package boundaries. So Haskell has this notion of packages, and if you want to think of modules as compilation units, then you can sort of think of packages as linking units, if you like. And these packages can depend on each other. So in this case, we have a package 2, and that depends on a package 1. And what that means is that modules that are part of package 2 are allowed to import modules that are part of package 1. But interestingly, it does not mean that every module in package 2 depends on every module in package 1. It only means that modules in package 2 are allowed to import some modules in package 1. So if we look at this sort of at the level of a build action graph for those two packages, where package 1 is blue and package 2 is green in this case, then we see that some of those actions are going to depend on some of those actions in the other package based on those imports, but not all of them. So not every green box here depends on all the blue boxes, right? Now, if we look at this picture and we imagine that the x-axis on this represents time, sort of how we schedule build actions, then we do see a bit of an issue here. And the issue is that we first have to completely build the blue package before we can actually build the green package, even though a bunch of the module compilation actions in the green package could be scheduled far earlier. And this was indeed a problem that we ran into. And the reason for this was that we didn't have a good way of sharing the module granular dependency graph from the blue package with the dynamic action of the green package. I mean, there were some stunts you could pull. You could like serialize it into a file and then parse that file later on, but there was no fast way to do this. But what we really want, if we still imagine the x-axis being time here, we want the green actions to sort of shift left as far as possible based on their dependencies, right? That's what we really want. So the way we were able to achieve this was by adding a feature to Buck2, which is dynamic values, and then the meta team kindly improved the API. With that, what we get to do is within a dynamic action, you can, similarly to a rule, you can return providers, and then where you invoke that dynamic action, what you get back is kind of a handle onto those, sort of like a future, if you will. And you can stuff that somewhere in some provider, and then in another targets rule that depends on this, you can pass that handle to a dynamic action as a dynamic value attribute. And then within the dynamic action implementation function, you get to inspect the results of that dynamic value. Because at that point, you are in the scope of that dynamic action that is being executed right now, and this also tells the Buck2 that it has to execute that other dynamic action first to have all that stuff available. And then this way, you can pass forward efficient representations of module dependency graphs and things like this through T-sets, which is Buck's equivalent of dep sets. And with that, achieve indeed this kind of build graph. All right. So let's look at a few cases of what this looks like in practice. So one thing we did was for last year's Haskell Implementers workshop, we took an open source Haskell project called Amazonka, which is a library with AWS bindings. And it's a reasonably large Haskell project with some 3.8 million lines of code and 35,000 modules. And building it with the native Haskell build system Cabal on my laptop with 8 cores takes a bit more than an hour. And building it on my laptop with Buck2 in a clean build takes 2 hours. So, okay, we'll talk about that a bit later. But the cool thing is that if we use a remote execution cluster with 100 cores, then we can build it in 15 minutes. And as we can see in that graph there, the utilization is also very good thanks to this module granular builds across package boundaries thanks to the dynamic values. With a dip there, I'm not exactly sure what happened there. That wasn't reproducible. I assume just the cluster was busy with something else in that time. We get that. We get the remote execution and the horizontal scaling. And then also incremental builds work very well. So I tried some different incremental workflows and comparing some of them, like one of them with Cabal took 7.7 seconds and with Buck2 1.4 seconds. So we get very nice incremental builds. And of course, we also get to benefit from remote caching. And then, of course, the use case that the project was all about at Mercury is also a large Haskell code base, some 1.8 million lines, 18,000 modules, and growing. And Cabal builds on CI around above 25 minutes, deployment cycles above 1.5 hours. And with the Buck2 build there on CI, more than 90% of the actions are cached. And for local developments, typically, it's even more than 99%. So a lot of benefits from the incrementality there. All right. There are a few other topics I want to look at more briefly in the interest of time. So persistent workers was something I had mentioned earlier as sort of an initial attempt in the Bazel side to achieve incremental builds. But of course, the purpose for persistent workers is really to speed up compilation by avoiding repeated setup of compiler runtimes and stuff like this. And you saw that the Amazonka case, the Buck2 build was twice as slow as the Cabal build locally. And the reason for this is that the way that the Haskell compiler can be invoked in 2 different ways. Either you use it in so-called one-shot mode, which is to just compile one module at a time, or you give it all the modules of a package and it compiles them all at once. And of course, in that mode, the compiler only has to start up once, and it only has to read the information about package dependencies once, and then it can quickly build all the modules out. And with the incrementality at the module level that we want to have in Buck2 and also in Bazel, we cannot really have that. Instead, we have to invoke the Haskell compiler once per module. And that's where this 2x slowdown mostly comes from. So it's a penalty on the compiler startup, package loading, and a bunch of other stuff. And so the idea here is to have a persistent worker for the Haskell compiler so that we have a warm Haskell compiler and we avoid all that repeated startup overhead. And Buck2 does support persistent workers locally through a gRPC protocol. And for remote builds, we also added support for the Bazel remote persistent worker protocol. And This is somewhat still work in progress, but it's running at Mercury now, and a full build can go from 97 minutes to 21 minutes with this persistent worker. So it's clearly a big win. All right. Another topic I want to briefly touch on is the idea of recompilation avoidance. So with these interface files that I mentioned earlier, where when you compile a Haskell module, you get an object and an interface file, and then downstream you're going to depend on those interface files. They contain information like type signatures and symbols and things like this, but they also contain some other information that changes more frequently than you would want to invalidate downstream actions. So even if you make a change that doesn't impact the exposed symbols, you might still make a change to the interface file that invalidates downstream actions. And that's not something we want. And that's also something that the native build tool can avoid. And so both in Bazel and Buck2, there are ways to work around this. And the way to do this is a clever trick around unused inputs. So what you do is, the unused inputs feature is there for build action to say, oh, you provided me all those inputs, but that one I actually didn't read, so if that one changes, don't invalidate me, just keep the cached version. That's the idea behind unused inputs. So what we do is we take those interface files and we tell the build system they were all unused. And then we also take those interface files and we project out the information that is actually relevant for invalidation. It contains a field called the ABI hash. And we make that a used input. And so then if that field changes, the action will be invalidated. If the rest changes, it won't be. And that works both in Bazel and Buck2 because they both have this feature. And then no talk of mine would be complete without mentioning external dependencies. So in Bazel, we can do two things. One is if the Haskell compiler installation that you're using comes with its own set of third-party packages, then you can just import those. And we often do that with Nix-provided compiler toolchains and package sets. Or you can use Bazel to invoke the Haskell package manager and resolve and download third-party dependencies and then build them inside Bazel as individual build actions. That is something that we've implemented on the Bazel side. On the Buck side, so far we have only implemented the import through pre-built Nix-provided packages. But one of the reasons why on the Bazel side we really wanted to have the direct package manager integration is that if the package set is provided as by Nix as part of the compiler toolchain, then if you make any changes to your transitive closure of third-party dependencies, you're going to change the toolchain and invalidate all your Haskell build actions in your project, even if you only add one dependency that is only used by one target. That's clearly not ideal. But in the Buck2 case, thanks to the dynamic dependencies, what we get to do is we can dynamically inspect the Nix-provided package dependency graph and then wire the actions up in such a way that they're only invalidated if the actual package they depend on are invalidated. So then we also get package-level incrementality with third-party dependencies. And another neat feature it has is the Buck extension language, which is the Starlark API to add custom commands. And we can use that to query our project for third-party dependencies and then generate the import metadata we need for Nix and the Buck2 targets, sort of the boilerplate, to avoid duplicated manual efforts. All right. So back to Bazel and in particular dynamic dependencies. So what sorts of languages benefit from dynamic dependencies? Obviously Haskell is one of them. I've talked about it at length. OCaml and the family of languages there can also benefit from this. It sort of has similar properties. There are a bunch of other languages as well. But C++ 20 modules also have this kind of property where, you know, when you compile one module, it produces information about the interface that other module compilations are going to need. And I saw that C++ 20 module support, and was also mentioned earlier, was merged into Bazel. And that's, of course, implemented in the built-in C++ rules in Java. And from what I understood when looking at the code, it also uses Bazel's capabilities of restarting actions to achieve a form of dynamic dependencies. For those that remember the build systems a la carte paper, you might remember that Bazel is classified as a build system with dynamic dependencies in there, even though the Starlark API, of course, does not expose this. And well, as rules Haskell authors, we would like to have that, but I've been told that would be very, very, very difficult, so we'll see. All right, that's all I had, so thank you very much. Again, I work at Tweag by Modus Create. We help people with Bazel migration, so if you need some help, let us know. And we have a booth over there, so come over and talk to us. Thank you very much. And maybe we have some time for questions?
Hi, thank you for the talk. So this is probably a very noobish question. Why can't we just have Haskell libraries compile individual source files like the module level instead of at the package level?
Right, so essentially the Haskell module rule would be doing that, right? If I understand the question correctly. So if I find the slide, this one, right?
Oh.
Then you would have, okay,
sorry, I
it's
missed
invisible.
Sorry.
Then you have a rule for building a single Haskell module, and you expose your module dependency graph to Bazel in the build file, and then the Haskell library target says, I depend on those modules. And then if you want the cross-package thing, that's where things get really icky, because so this is noisy and annoying, and with Gazelle, you can auto-generate it with the CPP limitations, but it's still noisy in the diffs and all. But now if you want the cross-package module granular builds, then at this Haskell library target here, it's not going to be enough to say that this Haskell library depends on that other Haskell library. You're also going to have to somehow say that module B depends on module J of that other library and so on.
Because this is how sort of, I guess, C++ works right now in Bazel. I guess there's no big difference or distinction between a module and a library. There's kind of just, I guess in Haskell you have these like two layers of concepts, whereas in the current non-C++ 20 module thing, there's only one, which is the CC library.
But in C++, you don't have the issue, because in C++, if you have a CC library target that has 100 .c files as sources, you can compile those independently. And if you change one of them, you're not going to invalidate the other ones.
Whereas in Haskell, you might, right?
But if you have a Haskell library target with 100 modules in them, and you change one of them, and then you have to rebuild the other 99, that's not so nice.
Right. OK, thanks for the explanation.
Sure.
Hi, I'm mostly curious about the motivating use case behind this work and the evaluating Bazel and evaluating Buck2. Like, was there a use case here where it did actually make sense to move a project from Bazel to Buck2? And what was the size of that? And I assume that is not a reasonable thing that most projects would be able to do.
Yes, so the use case was going from the native Haskell build tooling to something faster. The size of the code base is there, 1.8 million lines, 18,000 modules. And what we did do was we did evaluate both. So we did evaluate a Bazel setup with the automation and the Haskell module stuff. And that was just noisy, and when you do development on Haskell projects, the module dependency graph can change relatively frequently. So that is just not so nice maintenance overhead. Okay, and the team is also here if you want to chat.
Cool, yeah. So it was a Haskell mono repo and trying to get faster builds. OK.
That's right.
Cool, yeah, thank you.
Welcome.
Hello, I was curious with the persistent workspace that you mentioned, how you ensure deterministic builds that you don't accidentally end up using something that was put in there by a different action that you didn't declare as inputs.
Right, so with a persistent worker, that is indeed a problem, and essentially the answer is you have to make sure that your persistent worker doesn't do that.
I know that a bunch of languages have that, right? C++ and C# and a whole bunch of other stuff have that.
I mean, Java in particular has the persistent worker, right? I'm not so sure about C++. I wouldn't know.
I think it's the shared symbols or something. At least MSVC or something has it.
OK, maybe there is a thing, yeah.
But
yeah, I mean, what you're doing is you're persisting state in memory and potentially on the file system across build actions. That's what you're doing. And you're sharing that state across build actions. Right. And if you're doing that wrong, that's going to produce issues. So yeah, don't do that.
Sure.
Hey, this is a Pretty interesting talk. I was interested because it feels almost like you're creating a subgraph over the top level target graph, which is much more finer grained and is dependent on individual components that are contained within the targets themselves. How does a downstream target module know about the existence of other modules? Like, do you expose every single module as a part of an info provider and essentially they all get lazily resolved? Do you run into any issues like if a downstream target tries to do like a to list on a depth set, you end up accidentally evaluating and waiting for everything to resolve? Do you have to be careful about things like that? And what's your unit of caching at that point? Is it at the target level or is it at the module level?
Right, yes. So, I mean, the property that there are two different graphs is kind of shared between Bazel and Buck2, right? You have the target graph
One of them
and
is
the
the
action
sky
graph.
graph and the other one is the target graph, right?
Yeah, exactly. And it's just that in this case, you get to dynamically generate parts of the action graph. So the action graph in the beginning kind of has these black box actions in them, and then during the build, they get resolved and replaced by the fine-grained actions that are part of them. But it's still within the action graph.
I see.
And then the way these dependencies are exposed is through the usual providers interface. So on the target level in your bug files, what you're going to do is you're going to say that library has a depth attribute, and in there you list that other target. And that's what it looks like there. And then in the implementation, you're going to look at the providers that these targets expose, and they're going to have the necessary information about the individual module. So like there's going to be some key values list in there, or
right.
dict in there that exposes the module information. And then we're using these dynamic values to forward the module dependency graph that was dynamically resolved between the scope of the dynamic actions. So within the rule implementation itself, you cannot inspect that yet, but you can forward that handle to the dynamic action you generate, and in there you get to unpack it and wire things up.
I see. Got it.
Okay. And the interface for that is then T-sets, which is the equivalent to depth sets, and it works pretty much the same way.
I see. Cool. Thanks.
You're welcome. All right. Thank you.
All right, another round of applause for Andreas.